6, 7, 8. So that'd be, oh, what? 3 times 10 to the 8th power. What number is that? That is exactly the speed of light. Whoa. Notice, we already put that on our notes. So we could have been able to predict this. We'll talk about it next time. And what frequency means is how often or how frequently a wave passes through any given point. Meaning, like, how many waves there are. So how often, how frequently, a wave passes through a given point. And then the velocity of a wave, we usually will denote this with c for this unit at least. If you go take physics, you might denote these things with different variables, but for me, we're going to make it easy. Yeah. Hertz, Hz. Sorry. So that's the full name for it, Hertz, but then Hz is the abbreviation. Yes, measured in Hertz. So the velocity of a wave, it's basically just the speed of a wave. We measure this in meters per second. Yes. I think so. You want me to flip it? Alright, well, let me try to flip it. Not that. Is that worse? I think that's how it was. Yes. Hz. Yeah. That's wavelength. Is that better or worse? I know it's too bright, but is it better for seeing the board? How's that? This is literally how it was at first. This is exactly what it was. What happens is because my pen is like it has a black thing, when it goes up there, the contrast gets messed up. So every time I pull it back, I'll try to. I can just reset it every time. Is it a good question? Okay. That is a terrible question. Ask the 100 people that I have already repeated this for 12 times. Hertz. H-Z, H-E-R-T-Z-S. Sorry, H-E-R-T-Z is Hertz. And then this is H-Z. Yeah, bad question. And now we have it on record that you're asking bad questions, wasting my class time. Because I've already answered that question no less than 3 times during this class period. During the last 3 minutes. Yeah. It is measured in meters per second. Okay. Measured in meters per second. Something important to note is that the velocity of all waves in a vacuum is constant. So you can kind of think of this c as constant, but we'll talk about it. And the velocity of all waves through a particular medium is constant, meaning all waves through air is going to be constant, or all waves through water is going to be constant, or all waves through a certain metal is going to be constant. So velocity is constant. So on your test, there's definitely a question that asks about all waves are going to have the same blank. And then your answer is going to say something to the effect of either velocity or speed. Not all waves will have the same frequency, not all waves will have the same wavelength, not all waves will have the same anything else except for speed, aka velocity. And so velocity is what we use to denote the speed of light. So c is the speed of light, which is a constant. This is 3.0 times 10 to the 8th meters per second. You don't need to memorize this because it's on the formula sheet. And then in this box, I don't know why I gave us so much space, mostly just to take notes for it. But your equation that we're going to use for this is that c, which represents what? Good. Speed of light is equal to f, which is my frequency, times lambda, which is this little upside down y looking symbol. We call that lambda. If you remember the first day of school, I gave you a paper and introduced that variable. So lambda is the other one. That's what we say. That represents wavelength. So c equals f times lambda. So if you wanted to write it clean, c equals f lambda. That is the equation that we are using here, where c is your speed of light, f is your frequency given in hertz, and then lambda is your wavelength. It needs to be in meters. We didn't define wavelength on here because the definition is literally just the length of the wave. So this is what Ferris asked about, like measuring from peak to peak. So we call it either from crest to crest or from trough to trough. That is your wavelength. It is literally the length of the wave. How long is your wave? So we measure it in meters, which is a unit for length. And then I want us to draw two different waves. The first one, we're going to do just one full wavelength on this line. So if you start on your line, kind of our 0 point, and you draw one thing up and then to the same order of magnitude down, or as close as you can, I know mine's not perfect, that is one full wavelength. And then on my other side, I'm going to draw like several waves, and then we'll stop it there. That is terrible. Sorry for the drawing, but just try your best. It will still accomplish what I'm trying to get across, which is that if you are looking at these, and I'm telling you that the length of the wave is either measuring from like here to here, so crest to crest, or from trough to trough, that length or that length. If I drew these perfectly, these lengths would be the same. Which one is it, wave A or wave B, has a longer wavelength? A has a longer wavelength, so I'm going to do increased or longer wavelength. That corresponds to a low frequency. Because there are not that many waves on here, it's not going to pass through the same point as frequently or as often. So a long wavelength means a low frequency, or a low frequency means a long wavelength. So like a radio wave, yeah, would have a low frequency. Yes. And then wave B represents a shorter wavelength and therefore a higher frequency. And then to tie this in with what we're about to get to, which one of these, I feel like it kind of makes sense if you just look at them. Which one looks like it has higher energy? Low frequency or high frequency? Does wave A or does wave B have higher energy? B, the higher frequency means higher energy. So with this, put lower energy for this one. Lower energy, can you see that at all? Maybe. And then higher energy. So we're kind of tying a third variable to it, where if I have high frequency, I have high energy. If I have a low wavelength, small wavelength, again, high energy. This one says wavelength and frequency are blank related. Are they directly related or inversely? Inversely related. It says frequency is V. We can change that to F. In physics sometimes, or in AP chemistry, they will use a V. So I try to be consistent, and then I forgot to change that one. So they're inversely related, but the relationship between frequency and energy is directly related. So if we look down here, low frequency waves would be things like radio waves, TV waves, microwaves. Then you get to like kind of medium frequency, and then the highest frequency waves are going to be X-rays and gamma rays. So those are the kind of the things that you're looking at there. We do put this graphic on the test, and you just have to be able to read it, basically. If you see high frequency, you should associate that with high energy. And before I even said anything to y'all, you pretty much knew this is the high energy section. This section has low energy because that's just how it looks. And then now we're going to attach colors to this as well. And so the wavelengths of different colors have been given to you down here. So the visible light spectrum falls into like kind of this section down here, where it's like medium high frequency. And then these are the colors that we can see. So this is like the human visible light spectrum, but animals can see different frequencies as well. So they have a higher or like longer visible light spectrum. Where if I'm looking at this end of our spectrum is lower energy, and this one would be higher energy. That applies to both the waves themselves and then the colors that we're talking about, meaning that this red is on this end, that's lower energy, and then violet has higher energy. And if you look, that is inversely proportional to the wavelength. If I have a shorter wavelength down here, that makes sense because I have higher energy. Longer wavelength, lower energy. No. Like, what do you mean by, like, is this how? Like, I didn't teach you a process. Mm-hmm. There's a whole optics unit in physics that talks about this, so if you're interested, I would suggest taking that class after pre-AP chemistry. No, no, I'm not offended. I don't think people who are colorblind are offended, or offensive. Okay. So, what you need to know is the colors in order of the rainbow and how much energy they have. So if you know the rainbow already, red, orange, yellow, green, blue, violet, or green, blue, purple, knowing that purple or violet has the highest energy and then red has the longest wavelength, lowest energy. Good? Okay, let's set up at least a couple of questions on this one. So it says, what velocity will UV light travel? So we're looking for velocity, which is what variable? C. Okay, so speed, C, has a frequency of this and a wavelength of this. Okay, so I have my frequency f and I have my wavelength of this, lambda. So I know my equation is C equals f times lambda. My C is going to equal f, which is 3 times 10 to the 16th hertz. And my lambda is 1 times 10 to the negative 8th meters. So this is why you grabbed calculators before you started. Type this in. So remember, when we type this, it's been a minute since we did scientific notation. If you type 3 on this calculator, it's going to be second comma for the E on your screen, and then your exponent is 16. And then you would multiply that by 1, second comma, and then when you type a negative, you need to use the actual negative button and not the subtraction sign, so negative 8. So I'm going to give you a minute to type this in on your calculator and see what you get. What? The star is the multiply button. I hit that. It's just a different calculator. Alright, when I hit enter, what do I get? Okay, how many zeros are there? 1, 2, 3, 4.